This video is about the example 12 on page 12 in chapter 1. That's the question which is about the geometry of complex numbers. So the question sounds like so. We have a complex number z, which is in absolute value less than 1. And we have to show that for such number, and I'll put a question mark over this implication, because that's the content of the question. We have to show this. We have to show that for such number, the argument of the quotient, 1 plus z on 1 take z, the argument of such quotient in absolute value always less than pi and 2. Okay, now this sounds like a complex numbers question, but in fact everything can be done in pure geometrical terms, and I have this diagram here which will help me to do that. First, in this diagram, I'll just look at this. This is the I have a circle here which is centered at the point 1. So this distance. In fact, I think I have a name for this point. That's the point A. Sorry, this is a point O, and that's the point C, and the distance OC is 1. So I constructed here a circle with the center at the point C with radius 1. That's the circle. Here it is. It's a big circle. That's the one. Now, further on this diagram, I constructed this number z. Here it is. So this is this blue vector. That's the one which represents number z. Because of this condition, absolute value of z less than 1, the end of this vector z, it stays within the bounds of this unital circle. Now, I also picture for you here the number negative z, which is the vector, like the vector for the number z, but which goes in the opposite direction. And now, what I claim is, because when you do arithmetic operations, plus and minus operations with complex numbers, in vector terms, this is just done like vector operations. So if I call this point A and if I call this point B, what I claim is that the distance or the vector array, in fact this is a vector, let me just make it a vector. Oops. Vector array. Let me do the vector, but let me do it properly. If it is a vector, OA is just a vector which represents the number 1 plus z, and vector OB, this vector, it represents number 1 take z. And let me also make this like a proper vector. Yeah. Okay. So these two conclusions is because when we do operations on complex numbers in vector terms, this is as if we do operations with vectors, and that's why 1 plus z will be this vector as a result, or this complex number as a result, and 1 take z will be this vector as a result. Right. Now, if you now look at the angles on this diagram, for instance, if you look at the angle COA, so if you look at this angle, then this is just an argument. You can now express this angle as an argument which connected with this complex number. So this is the argument of the number 1 plus z. Similarly, if you look at this angle, the angle COB, here it is, you can also express this angle as an argument of a complex number. Now the number 1 take z, here we go. It's the negative of the argument of the number 1 take z. Negative here is just because the argument of the complex number is negative when we go in the clockwise direction. And geometrically, angles are always positive. That's why we need the angles are always positive. So that's why we need this extra minus to make this inequality hold. Now, if you combine these two angles together, so if you look at the angle BOA, then this will be just a combination of these two arguments. So negative difference of these two arguments, and we know that difference of arguments corresponds to the argument of a quotient, like so. So angle BOA here, that's the argument of the quotient of number 1 plus z and 1 take z. And that's the argument here, the argument we looking at. So all we have to show that this angle BOA is less than pi on 2. How we can see that? Well, now it's easy. Now it's easy because now look at this, what I'm going to do. I'm going to name this point of intersection A1. I'm going to name this point B1. And then I can say that the angle, I can say now that the angle BOA, angle we're looking at, it is less or equal than the angle B1 OA1. Right? Just because one angle is strictly within the other angle. This one. However, the angle B1 OA1, that's the angle which is a part of a triangle B1 OA1. That's triangle which rests on a diameter. This is a diameter of this circle. And that's a triangle which is inscribed in your circle. We all know that such triangle is actually a right angle triangle. So it's a triangle which has 90-degree angle, and that's the 90-degree angle. So that's what I'm saying to you is that actually this last angle is 90 degrees, so pi on 2. And that finishes the proof. We needed to prove here that the angle is less. The argument is less than pi on 2. This is the same as angle BOA less than pi on 2, and that's how we see it. Then the question is done. So this